let's go to the introduction first. In logic, quantifier are words or phrase used in language to indicate the quantity or extent of a subject. They are often used to provide information about the amount or frequency of something.
There are two types of quantifier. The first one is existential quantifier and the second one is universal quantifier. For universal quantifier, it can be written as this symbol which is look like in the slide, and it look like double down A, and it can be read as for all, for any, and for every. For one variable, it will be for all x, px, or can be written like in the slide. And for two variable, it will be for all xy, pxy, and also be written in the slide. The statement for all x, px is true if all the value of x in the universe prescribed true, and the statement is false if there is any one value of x that described false. Now let's look the example of the universal quantifier. Let's determine the truth value of each statement. The first one, let all x consist of real number and x squared plus 2 equal to 0. So let x equal to 1, so it will get 1 squared plus 2 equal to 3. So it is not 0. So the statement will be false. The second example is let all x consist of whole number and x squared more than x. So let x equal to 1, so 1 more and equal to 1, so it is true. So it proves that the statement is true.
Existential quantifier can be written as backwards x. For some x, px can be terms like in the slide, and for some x, y, px, and y becomes like in the slide too. For the true value will be depend on the universe prescribed, and for some x, px will be true if there at least one value of x from universe prescribed that makes px true. Existential quantifier can be expressed as for some x, for at least one x, and there exists an x such that. Let's move to the example given. We must determine the true value of each these statements if the domain consists of all real numbers. For A, for some x, x cubed equal to -1. And for B, for some x, x power of 4 is less than x power of 2. And for B, we must let x equal to 1 over 2. Then we calculate 1 over 2 power of 4 and 1 over 2 power of 2. And we will get 1 over 16 is less than 1 over 4. And it is true. So for some x, x power of 4 is less than x power of 2 is true.
After we know about the quantifier, let's go to the nested quantifier. Nested quantifier is a mathematical statement that contains more than one quantifier, which is that the quantifier is in a statement, it have two or more. So in mathematical statement, we should read the quantifier from left to the right. So generally, there are 4 combinations of nested quantifier, which are first, for all and for all, and second, for some and for all, third, for all and for some, and lastly, for some and for some. So how to read the nested quantifier? Firstly, let me try to read the first statement, which is for all and for all. So how to read it is for every value of x and y such that blah blah blah. So the condition is where for every value of x and for every value of y is true. then the statement is true. Second, we go to the for some and for all. So how to read the mathematical statement is that contain the nested quantifier is there exists value of x where for every value of y such that blah blah blah. And the third one is for all and for some. The statement that contain for all and for some can read by for all value of x there exists a value of y such that blah blah blah. And lastly, the mathematical statement that contain a quantifier which are for some and for some. So how to read it is there exists a value of x and y such that blah blah blah. So there are how we read the nested quantifier to make it easier understand when it have nested quantifier.
So now guys, let's go to example for nested quantifier. Now we have pxy for 2x minus y equals 1. So we need to determine the truth value for all x for some y pxy. So guys, the universe set for this example is infinite set. Thus, the solution is by construction. Suppose that we take any integer x that exists integer y such that y equals to x minus 1. For example, let x equals to 1, so we will get y equals -3. We can try other integers for x. Therefore, the statement for all x and for some y, pxy, is true.
So now let's go to the finite set. To find that the truth table value of for all x for some y pxy such that x plus y equals to 30, where x and y are equals 6, 7 and 8 inclusively. The prescribed set for this example is finite set. So one way of solution is by using the table. For instance, as shown in the table beside. As you guys can see at the table, we will substitute for all x and for some y with the numbers 6, 7 and 8. Thus, when we see at the truth value, we only got 2 true value for each numbers, which is 13. Now, since not all x with at least one y that give true value, therefore, for all x and for some y pxy such that x plus y equals 13 is false. Now, let us change the quantifiers to for some x, for all y pxy such that x plus y is 13 and remain the same universe set. Observe the following table beside. And as we can see at the table, we still get 2 truth value, which is 13. For all x and for some y, 6 plus 7 equals 13 and 7 plus 6 equals 13 only. So in conclusion, since there exists not even one y for all x that give true value, therefore for some x, element of integer, and for all y, element of integer, such that x plus y equals 13 is false.
Alright guys, let's we move to the last subtopic, which is the negation of quantifiers. I will explain about the rule. This rule for negating statement with one quantifier. There are 4 conditions. First, negation of for all x px logically equivalent to for some x negation of px. Next, negation of for some x px logically equivalent to for all x negation of px. The third one is negation of for all x negation of px logically equivalent to for some x double negation of px is logically equivalent to for some x negation of px. And the last one is the negation of for some x negation of px logically equivalent to for all x double negation of px is logically equivalent to for all x negation of px. Next, I will explain about example for negating statement with quantifier. As I stated here, is only one example. The question, we will negate the question. The question asks us to negate for all x for some y, x plus 2y greater than 0. So we negate all the statement that we got. For some x, for all y, x plus 2y less than or equal to 0. So guys, based on our group discussion, we can make a conclusion that logic and proving are important, improving the quality of life. There are proofs that can introduce the technique to solve the problems that we are facing. That's all from our group. Thank you.